minimum step angle. So step motors. So here are the objectives of this lecture. First, we want to learn different types of step motor, the constructions. They have several constructions also. So different types of the volume used in step motor. Understand the different types of drive sequences used. And so in the brushless DC motor, we talk about the driving. This is the circuits. Here we are going to talk about driving circuits for step motor as well. And we learned the torque speed relationship for the stepper motor. So here is the step motor. So this as you can see, so here is this is a circle, and here is the permanent magnet. The basic permanent magnet step motor. So it consists of stator, and this is a stator with two sets of coils wound on a pole. This is a fixed housing. So this housing is a fixed, and a rotor that incorporates a permanent magnet. So this is a rotor. This guy is a rotor. Rotor means it rotates. So this is the outside housing is a stator. Stator means that this guy remains stationary. This guy does not move, does not translate, does not rotate. This guy is rotating. So we have for this specific case, we have 4 poles, 4 pole pieces, 1, 2, 3, 4. As you can see, so here is A minus, and here is A plus. It means that so these 2 poles, this one and this one, they are connected together. You can see also here is a common point on lowercase a. Lowercase a here, this lowercase a. It means that physically these 2 guys they are connected together. Make sense? Okay, so the same thing for these 2 pole pieces, the B plus and B minus. One is a cathode and one is anode. Also, we have a common point lowercase b. So these 2 coils, they are physically connected at the point B, lowercase point b. So, so this is the same basic structure as the permanent magnet, the brushless DC motor. Brushless DC motor, we also have a permanent magnet, which is connected to the out of the shaft, and they are in the middle. So, this guy is also in the middle, and it differs from DC in that the rotor rotates to given positions, stop and hold that position. For the brushless DC motor, when you energize the coils, and the output shaft will be continuously and rotate in one direction, right? But here is different, and here you can just go to a given position. You can specify the position, how much angle you can go, and then you can stay there as long as you want, and then you go to the next step. So that's the beauty of step motor, and you can precisely control the position. Is there a position you want? If you want to do something, you can just go to that position and do something. For example, in my laser cleaning lab, in the machining lab, right? So we have 2 step motors, which controls in X direction, and another one controls in Y direction. So if we want to machine this part, right, in one part, we can just go. We can just specify how many steps you want to move in either in X direction, in Y direction, and then you just stop. After you finish the machining at this point, you can go to the next desired locations. Okay, that's the beauty of step motor. For the DC brushless DC motor and the brushed DC motor, they are usually for continuous output shaft torque. But this one, I can go position, then I do something. Another position, do something. Another position, do something. So this is very, very beautiful property. So here, how this works, I'm going to show you guys how it works, and also the basic principle is still the same. So when we have two, this is electromagnetic fields, and these two fields are going to interact with each other, and they will generate this mechanical force. Still the same principle, right? But here I'm going to show you how it works. Look at here, guys. So look at here, okay? At the very beginning, so these two guys, they are not energized. And so here at this point, so these two pole pieces, they are connected together, and these two guys, they are energized, right? And they are energized, and we know that. So this is the permanent magnet, north pole and south pole, and we know that in physics, when we have two magnetic fields, the north pole of one field and always want to attract the south pole of another field. You guys agree? That means NS, they are contracting each other. NN repelling, SS repelling. You should know that, right? So in physics, we have these different poles, they attract to each other, and the same polarity, they repel each other. And you need to keep this in mind. For here, guys, you can still use your right-handed rule. The right-handed rule means that when you check the polarity of a coil, and so these four fingers denote the current direction, and then your thumb will point to the north pole of this newly generated field. Do you guys still remember? Still remember, guys? As I said last time, we only use the left-hand rule when we just determine what is the mechanical force direction. For all other principles in physics, we use right-hand rule. Sometimes, guys, and for example, here, okay, if this is the cathode, that means the current goes in this way, and then come out this way. Then I can use my right-hand rule this way, right? Because this is the current direction. This is the current direction. Then for here, my thumb, it goes up. It goes up means that here will be the north pole of this newly generated field, and here will be the south pole of newly generated field. You guys agree? Right? So the same thing here. The same thing you can see. This is a V minus. This is a anode, and so here it goes in this way, and goes in this way. I'm still use the right-hand rule. So here from left to right, and this way. So still here for this pole piece, and still here this is N, and this is S. Right? So as I said, different polarities, and they attract each other. The same polarities, they repel each other. As a result, and this south will attract this N, and this south will attract this N. That means if you analyze these two poles, so this is the rotor here, which is the permanent magnet here. It is fixed in this position. Yes, guys? How can these guys stay in that position? Because the interaction between the permanent magnetic field and this is the newly obtained magnetic field. And they attract to each other and then have this position. Now, as a result, so this is the orientation of the output shaft. So in next instant, I de-energize these two guys. But I energize these two guys. The same thing, right? Again, the same thing. You use the right-hand rule. This is the cathode. This is the anode. Still use the right-hand rule. So this is N. So this is N. Here is S. So here is N. Here is S. And you can just think N S N S. Then so this field disappears. and then this N will be attracted to this position, so this S will be attracted to this position. As a result, and in the second instant, this is the orientation of my output shard. Make sense? Okay, the same thing. The same thing. 1, 2, 3, 4. As a result, as long as you just do the sequence of energizing, de-energizing these two poles, and this is pole A and pole B, and no, I will not say this is the two the sets of the coils, the group 1, group A, and group B, and you can get you can go to the desired location. Right? So also, as I said, when we come here, if we just keep this is energized, and then this guy will be the position will be fixed here until you do something else. Move, stay, do something else, and then you can move again. Questions so far? No question? No question. And here are two different the concepts. The holding torque. The holding torque is the maximum torque that we can apply without causing the rod to break or free of its position and rotate. And this is the holding torque. And holding torque means that when my output shaft is fixed in this position, how much torque you need to apply and to let this guy move. Okay, and here is the type of guys, and without causing the rotor and to break free, without. So this is the first concept. A second concept, detent torque. Without any power applied, if you do not have apply any power, and this is a stepped is APM step motor. So a PM permanent magnet step motor, it still has some holding torque. So this holding torque is referred to as a detent torque, even before you energize it. And so these guys still have some residual torque. If you want to make it move, and you need to do something, to apply some more. You understand that? Okay, so there are two different concepts. Let's see, here is a holding torque. This is a holding torque. This is a one step, the holding torque. So here is one equation to calculate the number of steps per revolution. The number of steps per revolution. So this S equals and 2p lowercase p n poles. So p is the number of phases, and the lowercase p. Okay, lowercase p is the number of phases. N pole is the number of poles on the rotor. So for our case, and the number of phases we have 2. The poles is 2. That's the reason. The poles number of phases. So this is a 2p n number of poles. Then we talk about this is internal wiring, and we know that so the direction of the current is very, very important. And then we talk about how we weld. So here is A and B. So this is the two wiring. Sorry. So A and B. So the A and B there. The 2-phase and the 3-phase motor. So here this one, okay. And this is a two-phase, one phase, two phases. So here B is a three phases. This one is a three phases. Respectively, this is a single coil, right? So this is a single coil on each pole. And write down. I want you guys to write down. So this because based on my teaching experience, so here is very, very confusing. And so you can see these two guys. 1, 2. Can somebody tell me what's the difference between these two guys and these two guys? What's the difference between these two guys and these two guys?
The amount of capacitors.
Not capacitors. So this is the coil.
Okay.
Right? So the difference between these two and these two is that for one pole we have two weldings. Two weldings. But for here, for one pole, we have only one welding. Guys? So this is called monofiller weld. Monofiller weld means that on one pole we only have one welding. Write down this. Monofiller means that we only have one coil on the same pole. So B, C, and D, they are bifilar. And bifilar means that one pole I have two different weldings. I have two different coils. That means for this guy, I just need to change which welding I'm going to use. I do not need to change the current direction. But here, if I want to change the polarity, I must change the current direction. One more time. For this monofiller, for these two guys, if you want to change the polarity, that means N and S, if you want to change these two guys, switch these two guys, you must change the current direction. However, for the bifilar, I do not need to change. If I want to change the polarity of the pole, I do not need to change the current. What I need to change is I just select which coil, which welding I use. So that's the reason this guy is called bifilar. Bifilar means that on one pole I have two weldings. This is one pole, okay? This is one pole. You can see this one pole, right? So this I use the right hand side. So this is north. For this guy, if this is a cathode, and this goes in this way, so I need to use the right hand rule this way. So this is N, this is S. So both of them, and actually they are the same pole. They are monofiller. Monofiller means on the pole only have one single. This is welding. You understand, guys? Are you guys okay? So the fifth one, the E is a lot. In last slide, we include two cases. A is a universal wound two-phase step motor and universal wound four-phase motor. And for the previous one, it is kind of misleading, kind of confusing. And however, when it is good to us, to the customers, that whenever you buy something and in the data sheet from the vendors, and they will give you all the details. So here is a driving step motors. So now we come back to see the driving step motors here. The driving step motors. This is a step motor. And can somebody tell me what this is, a monofiller or bifilar, guys?
Monofiller.
Why?
Because there's only one coil per pole.
Yeah. Some people didn't. So this is only one single coil or single welding on one pole. So this is That means it means that if you want to change the polarity of this guy, and you need to change the current direction, right? Okay, so this step motor involves two distinct parts: the drive electronics that produce a current flow in the coil, and the sequencing electronics that determine the order in which the coil will be energized. So this is because you want to get the desired location, and you need to correctly sequentially, and to energize this is the different phases in a very good manner. So this red figure shows the drive circuit for two-phase monofilar wound-step motor. So this guy, all right, this is a half bridge, right? Half bridge. This half bridge contains NPN transistor and PNP transistor, and this is sticking, and this is the sourcing. Right, guys? Do you remember last this Wednesday, Monday? I talked to you. We refresh our memory. This is the NPN, this is the PNP, and how this works, and both of them are still, and we compare the voltage between the base terminal and the emitter terminal. For here, this is emitter terminal, and for the PNP, this is an emitter terminal. If the voltage difference between the base terminal and this is the emitter terminal is higher than the threshold value, and then this transistor is turned on. Turned on means that the current flow is allowed. Alright? So you can, for here you can just see. Like for example, the need to produce a drive of two polarity gives rise to the concept of bipolar. But it requires a full H bridge for each phase. And write down, guys, we have learned this is monofilar and bifilar. Monofilar, bifilar, monofilar and bifilar. So these two guys are talking about the welding on the pole. So now here's another concept: bipolar. Right? So this the need to produce drive of two polarities to concept bipolar, and this requires a full H bridge for each phase. For this phase, we have this one, and we call the full bridge. And for this guy, and we have this half bridge, and we still call this one as a whole bridge. I'm going to show you on how it works, guys. So suppose guys, at some point, so this phase, the voltage is lower enough, right? The lower enough, that means this guy is emitter. The difference between these two terminals is higher than the threshold value. Then the current can go through. Also, simultaneously, in the meantime, so this guy is open. So this, I'm sorry, I will not say open. So this guy here, this is the voltage is higher enough such that the voltage difference between this base and this is emitter is higher than the threshold value, and then this guy will be turned on. If this guy is turned on and this guy is turned on, then the current can go this way from the top to the bottom and come down to the ground. What? So as a result, the current for this phase, we have the current direction that goes down. That goes down. Now, if we want to change the polarity, as I said, this is a monofilar. Monofilar means that on the pole you only have one single coil. One single coil means that if we want to change the current direction, change the polarity, you have got to change the current direction. So as a result, if I want to change the polarity, I want my current to go from the bottom to the top. You guys agree? from the bottom to the top for this phase, it means that I want this transistor to be turned on and this transistor to be turned on. And however, this guy is shut off and this guy is shut off. You understand? So this is the monofilter. Monofilter corresponds to bipolar. Write down this. Monofilter corresponds to bipolar. The same thing. And for the second phase, and we have this half bridge, this half H bridge, and this half H bridge. You understand? Okay, for each of these two phases, and we have a full H bridge. And even though we do not write them in parallel, but here this half plus half is a whole. Questions so far? You can see, and if you want to make sure this works, and you need to program. Program this is the step motor characters to drive the different coils at the appropriate time. But now we are very lucky. The vendors, the manufacturers, they have done most of us. Okay, so for us, everything is packaged, and everything is packaged. What we need to do is that we just write the program based on using their language, and then their language will be translated and to do this is to communicate with the machine directly. You understand? For us, and we do not need to drive this, drive that. But what we need to do is we need to use their language to write the program we are going to use. And there we call their compiler, and their toolkit will translate what we have written into the language they use to communicate with the machine. Understand? Otherwise, this step motor, the vendor, they will go bankrupt. Why? No customer will use it. All the customers, they just want to use it, don't want to learn it. You guys agree? But we are in the academia, we are different, and we want to know how it works from the bottom. But for other customers in our society, for example, when you do something for your garage, you use some step motor. Do you want to learn how it works from the bottom? No. I just know how can I write a program and to move my garage door upwards by the desired steps and going down by the desired step. This is what I need. I don't want to know how to drive this circuit, how to drive that circuit. I also do not care what kind of transistors they are using. Do you guys agree? Keep in mind, okay, so these are different levels. We are learning, we are in academia, we are learning the principles. That's the reason we talk about it so deep. But for other customers, they just want to know how to use them. They do not care how they work. Because why the reason I said this, because some students look scared when I say you need to drive the appropriate circuits, these transistors at the appropriate time. But don't be scared, okay, guys? You can see here is this is a bipolar monofilter. A monofilter is bipolar, right? Bipolar. This is second one. Second one is we can see here. This one is called a bifilter. Why this guy is called a bifilter? On one pole, I have two different weldings. I have two different weldings. That makes that gives me more convenience. Why? I have the same the cathode anode. I just select which welding I'm using. What? to change the polarity. I do not need to change the current direction. And for both of them, for both of these two coils, we have the same current. But because these coils, they are different. They are welded differently. So even with the same current direction, when you use the red-handed rule, the polarity is different. Make sense? That means for these guys, if we want to change the polarity of the coil, and we do not need to change the current direction, we just need to change which coil we are going to use. Physically, both of these two coils, they are welded on this is the pole, on the pole. Okay, so the drive circuit for two-phase bifacial wound step motor. The bifacial welding allows us to change the orientation of the magnetic field. Orientation of the magnetic field here is what I just told you, polarity. North, south. What? Polarity. Orientation of the magnetic field, the same thing. Without changing the direction of the current flow. And these motors are also referred to as unipolar step motor. And don't be confused. Bifacial corresponds to, this is the unipolar. So this is very, very important. As I said, based on my teaching experience, when I asked my students these concepts, they are totally confused. They said monofilar is exactly unipolar. No, just look at the name, uni and mono, and they are very, very similar. But in this context, we are talking about different things. So keep in mind, monofilar we call bipolar. Bifilar we call unipolar. What? So you can see it reduces the complexity of the drive circuit. And for the previous slide, for each of these phase, we have a full H bridge. But each account for here, so each phase is a two-phase has two weldings. We only need to have two transistors. And we substantially, almost half, we substantially reduce the complexity of driving circuit. You guys agree? Why we can do this? Because the current is the same. The current direction is the same. And the always go down. So I just use the NPN. And just to make sure this is the base voltage is higher enough, higher than this is the threshold value. And then so this can be open and I can have the oil have this current going through and then generate the polarity. Any questions so far, guys? Questions so far? No question? Then we talk about the stepping sequence for the step motor. For here. For here, guys. But at the very beginning, I energize this phase, then the shaft is fixed at this orientation. And then I just energize these two poles, and then I can track. So these are two poles, the electromagnetic field attracts, and this is shaft to this is desired orientation, and so on and so forth. And then you can see my motor will look initially here, then goes this way, then goes down, then goes this way. So that means my motor is rotating counterclockwise. Understand, guys? Okay, here is a very beautiful name for the wave drive. write down it underscore wave drive. And wave drive means that we energize a phase at one time, one phase and one time. And we have several modes. This is our first mode, wave drive. A wave drive means that if we have multiple phases and we only energize one phase at one time. So here is the stepping sequence for step motor. For this is for the monofeeder or bipolar. So this is the bifeeder or unipolar. And we talk about this one, right? This is the whole bridge for this phase. This is the whole bridge for this phase. And for this is the bipolar or unipolar, bifeeder or unipolar. And we have 4 individual the NPN circuits. So here is a bipolar drive, is bipolar, is a unipolar drive here. And how can we just generate this is the counterclockwise, clockwise or counterclockwise for both of these two cases. And you can see here, this is highlighted one, is this the consequence. So this one is energized. For second one, energized. This one is energized. Third one, this one. The fourth one is this. If we follow this consequence, and we will have clockwise rotation. However, if we go down from bottom to left, we'll have counterclockwise. The same thing for this one. What? So this is actually on how people control the step motor. So this is energizing sequence for wave drive. So we have a second mode, and first mode is wave drive. Second mode is the full step drive. What is a full step drive? We compare this one with a wave drive. For here, for this one, 2 phases are energized at one time. All right? Because we can imagine, because at one time 2 phases are energized, that means we have more torque. You guys agree? Okay, so the equilibrium position at each step, and we can see that the equilibrium position of this is the shaft is not horizontal, vertical anymore. Now it is a 45-degree with respect to the either the horizontal orientation or the vertical orientation. Why? Because you energize these two guys together, right? Right, guys? So this will attract N. So this also attract N. Suppose this is the magnitude of this is the field is the same as that of this one. Then this is equilibrium, right? So this is our second mode. 2 phases are energized at one time. So this is for 2 phases and how we to full step drive and how we sequence. This is the bipolar drive and the unipolar drive. The same thing you can see. And for this one, when we compare this slide with the previous slide, and for the previous slide, at one step, only one box is highlighted. But here, because 2 phases are energized together for one step, and we have 2 highlighted boxes. You can see this one is on and this one is off. Also, for the bipolar, we use the H drive, and for the unipolar, we use this is a four single transistors, NPN transistors to be exact. So this is the second step. The third step is the half step. So half step is this half step is a special, guys. And half step is a combination of full step and wave mode. And write down, guys. Our first mode is wave mode. Second mode is full step mode. And third one is half step mode. Half step mode means that I can combine the wave drive and full step drive together. Okay? That means for every 45 degree, I will stop. For every 45 degree, I stop. But for the wheel drive, and you have 90 degree stop, 90 degree stop, 90 degree stop. But for the full step drive, and even though your orientation is different, but you always one step is 90 degree. One step, 90 degree, next step. I'm sorry, here, this one, this, oh, my arm is broken. You understand, guys?
Yeah.
But for the full half step means I go 90 degree, 45, 90 degree, 45, I go all these systems. So I want you guys to know we have three modes: wave, full step, half step. So here is and because we know we talk about a lot of the good things about this is the stem of this step to step the motor. But some students might ask, Doma, are there any drawbacks? Are there any limitations of this guy? Yes. The limitation is that and sometimes we might miss some steps. What? And sometimes we ask this guy to go 45 steps, but sometimes this guy will not follow your instructions closely. It might go 44 steps and stop. It happens. So here is usually this data sheet and will be given by the vendor, and this given by the vendor. It shows several regions. You can see that the pull-in region, this accessor and the step rate, and this is the torque, is the corresponding torque. So this shaded area is called pull-in torque. What is a pull-in torque? Pull-in torque, we mean there's no missed step. No step is missed. I mean, this guy closely follow your instruction. And however, if the step rate is too high, that's another story. If the step rate is too high, and we have this area is called through region. And through region means that we might miss some step. Right? And for our daily life applications, in this region, totally fine. However, for some very, very precise applications, you are supposed to make sure your